So we are going to continue talking about chapter 4, which is about relationships between categorical variables. So yesterday we just looked at tables and found row percentages and column percentages, and that was more or less basically it, right? Plus some bar graphs and the longest 4 questions of your life. Yes? Okay. So what we're going to talk about today are a lot of phrases and words that come up in like the media when you hear about statistics. So the first thing is risk. So have you ever heard something like, okay, your risk is 2 times higher for getting lung cancer if you smoke cigarettes, or it's actually not, it's like 13 times higher, but something like that, right? So the way that you find the risk of something, this is going to be equal to the number of people in some category or things, because you gotta find the risk that like your dog is going to get sick, right? And they're not people, even though I feel like my dog's a person. The number of people or things in a category divided by the total number in your group. So, for example, suppose you do a drug trial and you want to figure out, okay, what is the risk that somebody's going to get a headache from this drug? You could take all your people who did the drug trial and figure out how many of them got headaches divided by the number of people who were in who took the drug in the trial. Does that make sense? And that'd be the risk of getting a headache on said drug. So people that had a headache divided by everybody who took the drug. And something else that comes up a lot is something called relative risk. And so how you compute this, so you're comparing 2 categories in this case. And this is equal to the risk in category 1 over the risk in category 2. This could be things like, this would come up in a phrase such as, men are twice as likely to get a speeding ticket. For example, you find the risk that men get speeding tickets divided by the risk that women get speeding tickets, and if that thing is like 2, it means men are twice as likely to get a speeding ticket as women. Or, you know, people in a red car, for example, something like that. So if 2 risks are the same, what is the relative risk going to be? 1. Does that make sense? If these 2 things are equal, something divided by itself is 1, right? When the category in the numerator has higher risk, as in that's a bigger number, the relative risk is what then 1? Greater. Yeah, this thing is bigger than that thing. This thing is bigger than 1. So then it's greater than 1. When the category in the numerator has the lower risk, the relative risk is less than 1. Okay. And often, the risk in the denominator is sometimes called the baseline risk, which is the risk for a category which no treatment or behavior is present. So, for example, it might be your risk of getting a headache while taking a drug versus your risk of getting a headache from life. Does that make sense? Like, life tends to give you headaches too, right? So it's all the time, right? In my case, all the time. Life. Okay.
Is that kind of like a control group?
Yeah, it is. So baseline risk is kind of like what would be the risk being your control group. It's a great way to think about it. So you have, risk in category 1 taking drug versus risk in category 2 taking placebo. Right? Yeah. So it's a great way to think about it, is that's often like a control group type thing. Okay. And then the percent increase or decrease in risk. I think that this one is best explained in an example. So I'll tell you, it's going to be relative risk minus 1 times 100%, and that's going to give you the percent increase or decrease in percent form, but we'll have an example and I'll tell you where the formula comes from in the example. Okay, so let's actually talk about some risks for a specific example. So we have the National Health Interview Survey. This is an annual national health survey of people living in about 35,000 randomly selected households in the US. And on the basis of this data, the CDC-NP, oh, there was a P in there, they estimated that 15.7% of boys and 11.2% of girls under the age of 18 had been diagnosed with asthma at some time. So it looks like boys have more asthma than girls, at least according to that, right? Possibly. So the relative risk of having asthma for boys compared to girls, to figure that out, you do, so relative risk, and you can't use R because R is something else, right? So I'm just gonna kind of spell it out. This will be the risk for boys over the risk for girls. So what is the risk for boys? 15.7% divided by 11.2%. And it doesn't matter if you make them into decimals or leave them as whole numbers as long as you're consistent with them. So do that division and tell me what you get. 1.4. You must get 1.4 approximately because there's more decimals there, right? 1.40179. Yeah, so approximately 1.4. So how do you think you'd see that in an article that somebody is writing about this? Fill in the blank. Boys are blank times more likely, yep, to have asthma than girls, or have ever had asthma. Have you seen stuff like that? Like, have you read stuff like that before? Probably. Okay. So percent increase is really related to this relative risk thing. So here's the basic formula, and we'll talk about why it is that thing that I told you. So percent increase, at least in this example, is going to be the percent of boys that have asthma minus the percent of girls that have asthma divided by the percent of girls that had asthma in the first place. I think you can think that since the previous one was boys compared to girls, this one also kind of compares to girls. So let's just fill in the stuff there. What percent of boys have asthma? 15.7. What percent of girls have asthma? 11.2. All over. And this gives you, I think, approximately 0.4. Is that? Now, this is not a percent, as in it's a percent in decimal form, so what would I have to have added in there? Yeah, I could have taken like this whole expression multiplied by 100% or moved the decimal over 2 places, right? So it's a 40% increase. What was the formula that I told you above? And I know, just checking that you remember.
Relative risk minus 1 times 1.
So let's try that. 1.4 minus 1 times 100%. Does that give us the same result? Yeah. So let's talk just briefly about why that's like that. So look at this guy. I'm going to uncombine that denominator. What I mean by that is I'm going to write that instead as percent boy over percent girl minus percent girl over percent girl. So this to there. Do you see that the percent boy over percent girl, that really was just this relative risk thing that we did? And what is percent girl over percent girl gonna be? 1. So that's where that formula came from. So that's why it's the relative risk. And then the whole times 100% is just so that you get a percent as your answer.
And in this case, because it asked us for the percent increase, that's why it's boy minus girl.
Yeah,
So
if it asked for the percent
decrease,
decrease, that would flip. But it's been a long time. I would have to double check what that was, as I don't know if it'd be over girls or boys in that case. The only thing you're gonna be asked about in your homework is percent increase, I'm pretty sure. Okay, have you heard about odds? The odds you're gonna win are 5 to 1. In which case, buy that lottery ticket, right? The odds you're gonna actually win the lottery are like, 1 to some big, huge number, so don't buy those tickets. So they compare the chance of an event happening to not happening, and they're usually expressed as a phrase with the structure A to B, and it is really a ratio, but you don't write it that way. You know what I mean by that? You don't write a fraction, right? You just write number 1 to number 2. That's how they're given. So suppose there's a 60% chance it's going to rain tomorrow, making the chance it will not rain 40%. What is this ratio expressed as a comparison? So give me it as an odds. Yep, so start with 60 to 40, which is the sort of like unreduced form, and somebody reduced it to 3 to 2. What that kind of means for if you have a bunch of, like a large sample of days like this, for every 3 that there's rain, there'll be 2 that there are not. Does that make sense? For like a large sample of days. And then the odds ratio, it takes these odds in various categories, in these 2 categories, like 2 to 1 and 3 to 5, and it computes a ratio of those 2 things. We won't do very much with this one, just thought it was good to expose you what it is. So when the odds are the same in 2 categories, what is this odds ratio going to be? 1. When the odds of an event are higher in the category in the numerator, the odds ratio is going to be greater than 1. Yep. And if the odds of an event are lower in the category in the numerator, then the odds ratio is going to be less than 1. Okay. So we've already talked about these, but just sort of phrasing it a little bit different way. For all of these measures, tell me the value that implies no difference between 2 groups that are being compared. So 2 groups are not different if the relative risk between those groups is 1. Odds ratio, there's no difference if that ratio is 1. How about percent increase? 0%. Okay, so let's actually look at like some numbers. So we have a study that's done to compare side effects for 2 different drugs used to treat some medical conditions, probably as hypothetical, because the numbers come up really nicely. 100 people are given each drug, and results are shown in this table. We're going to just look at the headache side effect, so at least for now we can ignore the nausea half of the table, okay? We're only going to care about the headache part. So find the risk of experiencing a headache for each drug. So for drug 1, what's the risk you have a headache? How many people got headaches?
10.
Out of 100? So that's 0.1 or 10%. How about drug 2? 0 point, or 5%. Is that all right? So relative risk. So find the relative risk of a headache for drug 1 compared to drug 2. So relative risk will be risk for drug 1 divided by the risk for drug 2. It's 2. The risk for drug 1 was 10%, right? Drug 2 was 5%. That is 2. So that means taking drug 1, you're twice as likely to get a headache. Does that make sense? Okay. Let's just write that down. So taking drug 1, twice as likely to get a headache as drug 2. If you're someone who hates headaches like me, you're like, oh, yay. Drug 1 looks overall kind of bad, doesn't it? Also, nausea is worse, so ain't nobody want to take drug 1. Okay, what's the formula for percent increase? Relative risk minus 1 times 100. So our relative risk was 2. So 2 minus 1 times 100% is going to be a... So it's kind of the same. There's a 100% increase. As in, take the risk for drug 2 and then you increase it by 100%. And the funkiest one is the odds ratio. And this happens very often, so I'm not going to dwell on it too much. So the way you compute this is instead of doing a ratio of totals, you do a ratio of what would be the things in your odds. Like the odds of getting a headache for drug 1 would be 10 to 90. Does that make sense? Write that as a fraction instead. 10 over 90. The other one is... Have you guys ever been told that when you do division by a fraction, it's the same thing as multiplication by the reciprocal? Yeah? Can I show you why? Because maybe you forgot. Maybe you know too, okay? I don't want to insult your intelligence, but do you agree that this is true? 95 over 5, 95 over 5. Do you buy that? And then what happens to the denominator? It cancels. And you see how this becomes 10 over 90 times 95 over 5? That's like why that rule is what it is. So, okay, that wasn't the point. The point was that this is 2.11. Because this isn't actually algebra, it's stats, and so I'm going to focus so much on it. But, here you go.
I don't understand how you just got 95 over 5.
As in, where did I get it from?
Yeah.
Well, because I have a ratio divided by another ratio. And back at some point in your life, we were told that division by a fraction is multiplication by the reciprocal. Never told that? Okay, well then you missed, something happened. So a common thing to do is multiply by the reciprocal, as in the opposite fraction, because when I do that, you see how I get 5 times 95 over 95 times 5, which becomes some number over the same number, and cancels out to 1 over to 1. And the reason I chose that number is because it's the reciprocal of this denominator 1. And so one thing that I kind of skipped is that it's like, it's like this business over 1. But over 1 doesn't really do anything, right? So it's just, I shouldn't have skipped that step. Okay. Here, to make my slide move. So given that you're allowed to use a note card on your quizzes and you can write the formulas down, can you do those things? Okay, great. So the next question is a little bit backwards. It's a little bit algebra-y. For a relative risk of 1.53, this one isn't so algebra-y, what is the percent increase? This one's quite straightforward, actually. So your percent increase was relative risk minus 1 times 100%. That gave your percent increase, right? So I think you're told all the information you have to know to find that percent increase, right? 1.53 minus 1 times 100%, which is 53%. there is an easy relationship there, isn't there? That's like kind of like 153%, so the difference is the 53. So how about this one's a little bit backward? I told you the percent increase and you gotta find the relative risk. So remember you have this relative risk minus 1 times 100% equals percent increase. Where does the 140 go? In for percent increase? Can I just call relative risk a letter? What do you want to call it? What letter? Q? Sure, or well, we can call it R just for now, okay? R minus 1 times 100% equals 140. Now if this were you, what would you do first? Divide by 100? Sure, that works. So divide by 100. So R minus 1, what's 140 divided by 100? 1.4. So then the relative risk was equal to 2.4. Okay. So the main point of that section is just to familiarize you with some of the vocabulary so you can understand things when you read them. Okay. The next thing is kind of a weird thing that happens called Simpson's paradox. So this occurs when you have some kind of confounding variable that messes with your results. And associations that are one way, like say like the risk of, or well, a great example where it looks as if women are being discriminated against, like they're getting into a college at a lower rate than men. When you break it up into categories in a specific way, they're actually doing better than the guys. And that's why it's called a paradox, because it just seems like these two things shouldn't happen at the same time, but they do. So first of all, have we talked at all about what an observational study is? Like a little bit-ish? What's your guess? It means did you take people and divide them into groups, or did you not divide them into groups and just look at them? Just look at them. Do a lot of staring. Just kidding. So this is a study where researchers only measure and observe. They don't assign treatment. And observe. They do not assign. And these kinds of things come with all sorts of problems. But one example might be that researchers might ask you, do you take a vitamin? And they'll observe, do you take a vitamin, then figure out what happens to you later in your life. They watch you as time passes. They didn't say, oh, this half of you is taking vitamins and I'm going to force them down your throat, and this half is not. You got to pick. And a confounding variable, this is a variable that may explain or mask a relationship. So the first example we're going to have is to just kind of guess what a possible confounding variable might be in a specific situation. So in the 1997 Marist College Institute for Public Opinion survey, 995 people were asked whether or not they had dozed off while driving. And of the Americans, 31% of the men and 12% of the women said that they have dozed off while driving. Do you think, can you think of something else other than just men are irresponsible? No offense intended. For what might partially explain this big difference between the sex of the driver and dozing off while driving?
If they were a commercial driver.
Yeah, I think that more men drive truck than women on average, probably, right? Yeah?
And men, not to be racist at all, but men
Sexist?
generally, sexist, that's the right word. Either way, something's being offended. Men sometimes have more hardworking jobs, like
Yeah, so,
working. and
I think I get what you, yep. So men may do more long distance driving, which might involve driving at night, right?
But they do more driving in general.
Yeah, men may
More
do,
labor
they may do more
intensive.
driving in general, yep, that's a good thing. As if they log more hours, they're more likely to fall asleep, right? That's a good. And I think another thing could be that maybe they do more night driving. Is that, probably is true. And I think that's kind of gets at what you were saying, right? As an at a time at which it is sort of like easy to fall asleep at the wheel, so to speak. Random fact, if you're in Moscow, Russia, and you're driving truck, you cannot go into the city until after like 11 p.m. There's like a second rush hour because it's just too crowded. So,
I know here in the US they have policies on trucks driving at night, like we have to only do a certain amount of hours a day.
all sorts of stuff, yep, which I know nothing about, okay, because I've heard it exists. So this funny thing that we're going to talk about in this little lesson is this thing called Simpson's paradox. And what this happens, let me write this down. So the direction of a relationship or difference is reversed within subgroups when compared to within the whole group. And I have a great example. Who likes coffee? Oh yeah, right? You know what? Coffee's good for you. No. Like, I'm pretty sure that, okay, according to some statistics, it actually is. Okay, so somebody did some kind of survey study thing, and they found that coffee, I think it was increased, I can't remember if it was cancer or heart disease. Maybe it was cancer and heart disease. Maybe it was both. I Googled this before coming to class a couple days ago and found an article in Time about it, okay? So this is the old study, okay? And so for a long time it's been told to people that, yeah, having coffee is like bad for you. You shouldn't do it because when people drink coffee, they have an increased risk of cancer and heart disease. Here's the good news. When they separated out smokers. Smoking is a huge confounding variable in lots of things. They separated out smokers. What happened then is that coffee drinkers had lower rates of cancer and heart disease. Yeah, tell me not to drink my coffee now. So do you understand the kind of the paradox here? When they look at the whole group, they found that, okay, you drink coffee, your risk for heart disease and cancer went up. But when they separate out into groups, and they separate out the smokers specifically, they found that, well, in that case, if I compare the non-smoking coffee drinkers to the non-smoking non-coffee drinkers, the non-smoking coffee drinkers had lower rates of cancer than those who didn't drink coffee. And that might have been true in the smokers too. As in smokers that drank coffee might have had lower risk of cancer than smokers that did not drink coffee. I don't know about that last one, but I know it was true for the non-smokers for sure. Does that kind of weird you out a little bit?
No.
No? Okay, well,
It weirds me
you can
out
drink
that
your coffee?
It weirds me out that they didn't sort out the smokers to start out with because
Like it's disturbing it took a while. Yeah. If you want to be depressed about never knowing what to do with yourself, read all sorts of studies about what to eat, because it's just like, they're full of confusing, conflicting, bad statistics. So, all right, so here is an example with actual numbers. So this is hypothetical, but they're similar to data from several actual studies. We have 2,400 women, and they are categorized according to whether or not they use oral contraceptives and whether they have high blood pressure. So people in the 800 category, they take oral contraceptives, okay, and then number with high blood pressure. So can you figure out the percent that have high blood pressure out of those that use contraceptives? How would you do that?
8%.
You did 64 out of 800, right, which is, I think it's 8% exactly even, isn't it? Those are doctored to work out pretty. Real life isn't quite that pretty. Okay, and those that don't use oral contraceptives, 136 out of 1,600, which is 8.5%. Tentative conclusion. Would be something like using oral contraceptives is associated with lower blood pressure. Do you buy that?
Sure.
Does that seem what the data suggests to you? Like, it is the case that people that do use oral contraceptives, the percent that have high blood pressure is lower in that group, right? They're not, I think so, 8% versus 8, it's not very different, right? So how, it's quite close, and one reason that that closeness might actually be a significant difference because the sample sizes are pretty big. But we will learn, I understand you're feeling that they're not really close enough, they're not really far enough apart to make a conclusion. That, I totally buy that. But if you were just looking at the numbers, you could say, okay, well, the risk is higher if you don't take birth control, right? That's what at least that seems to suggest. And the thing that happens, so one possible confounding variable is smoking, but with something like this, that's not the big thing. The big thing in this one is the age. So people that are older tend to have higher blood pressure, right? They also tend to stop taking birth control, yes? Okay, so this is what happens if you separate them out into two different groups. So ages 18 to 34. So what's 36 out of 600? What percent is that? 6%. Uh, 16 out of 400? 4%. And then 28 out of 200 is? 14%. And 120 out of 1,200 is 10%. Okay, so what happened in this one relative to the last one? In the previous one, the percent was higher in the don't use contraceptives category, right? In this one, it's reversed, right? So the thing to point out here is that the relationship let's say maybe from, I didn't call them A and B, but can I call the first table A just to make it easier? So that relationship is reversed. When separated by age, the percent with high blood pressure is lower in the non-contraceptive group. So it doesn't appear that taking oral birth control is really a good idea for, or a benefit for blood pressure in this case, does it? Whereas the other one kind of suggests that it might be a little bit of a benefit, right? So, just something to consider. And I think the next one is actually a pretty famous example. I said that lawyers love stuff like this because they can spin the numbers however they want to spin them to make their case, right? So here's an example of Simpson's paradox. This looked at the admission rate for men and women that applied to graduate programs at UC Berkley. There was suspicion that there might be some kind of sexism going on here. And this data is, the actual data is confidential, but this example uses similar hypothetical numbers. So here are the figures for acceptance, because what happened with this case was that there was a Simpson's paradox thing going on, but they can't tell you this, I don't know why you can't, it's from your book, but.
It's just funny, it's like suspected sexism, data's confidential.
Yeah, who knows? So let's combine these data, these two programs, into a single table and figure out what percent of men who applied were admitted and what percent of women who applied were admitted. So instead of having program A and program B, we'll just have an admit and deny category. Does that make sense? So we have, I'm gonna, whatever, okay, men, women. Instead of being broken into two programs, we're just gonna have how many men were admitted, how many men were denied, and how many women were admitted, and how many women were denied. So how many men were admitted? 450. How many men were denied? 550. That sounded too gleeful, sorry. How many women were admitted? And then how many women were denied? 325. Okay, great. Okay. So the percent of men admitted will be what out of what? 450 out of 1,000, exactly. Which is 45%, right? How about the percent of women admitted? 175 out of 500. Which is 35%, I believe. Is that right?
Yep.
Okay.
Does it affect the results if you have way larger of a number than the, like, versus, for example, the men versus the women, there's half as many women?
I think that that's one of the things that's required to make the Simpson's paradox work, but I'm not 100% sure. As in, I think one of the reasons that this paradox happens is because the two groups are so different in size. As in, I think that's something that's lurking in the background that's making this happen. So yes, I think a lot of the examples that you'll have will have various, the categories will have be sort of like unbalanced somehow.
Because I thought, isn't it a good idea to always have the same amount of.
But you can't force an equal number of women to apply for a program as men, right? So it's not like you can actually do that. And if you're doing, say, like, we'll talk about sample design at a different time. And so, yeah, in that case, it's good to try to keep things sort of even. But in stuff like this, it's not really possible to do so. Which sex was more, according to this measure, which sex was more successful?
Men.
Yeah. So men were more successful. And you're like, oh, maybe we're just gonna like them to sue. I didn't get in. You're being sexist. Okay, which maybe is true. But look at what happens when you split them into the table as it's given. Okay, so I'm gonna do the same thing, but for the different programs. So for program A, what percent of the women who applied to program A were admitted? So men, women. So what percent of men that applied to program A were admitted? So it'd be 400 out of how many? 650, which is approximately, or is it exactly 61.5%? It's an approximate 61.5%. Okay, for the women, it's going to be 50 out of 75, which I think is about Yeah, 66.7. Let's give it 1 decimal. Oh, is that a little bit surprising? Compared to the previous result? Previous result was that men were more likely to be successful, right? This thing, who is actually more successful? Girls rule. Crazy. Okay, let's do program B. So men, women, program B. So how many people were admitted? So 50 out of 350, which is about 14.3%. And for the women, it's
1.5,
which is about and that one, women were a lot more likely to be successful, weren't they? It's kind of a crazy thing, isn't it? So,
Basically, they just pile all the information together as a whole for the entire university.
which
We're saying
probably
more
is a
than
reasonable
50.
way to get information the first time through, right? I mean, it's, and in this case, obviously, the point of this sort of paradox, me telling you about this, is that you just have to check. Does that make sense? You have to check and see if I separate stuff out into subgroups, does the relationship reverse? It's a possibility.
I don't know if it's possible to answer this question, but do you think the numbers would have been better if they had done appropriate, like the same amount like I was talking about?
It's completely possible the fact that there are so many men who apply to that first program and like so few women. Does that make sense? That probably is something that's causing it, and it probably has to do with just what the program is. Okay. So last thing is explain how this is an example of Simpson's paradox, and then provide a potential explanation by guessing what types of programs A and B might be. So I have my own guesses. So the Simpson's paradox thing is that in the overall group, one group of people is more successful, but when you break it down, the other group is more successful. And that's what you should just write a sentence explaining. So what I said that in the combined programs, as in like all together, men appeared to be more successful, by which we mean more likely to be admitted. And you can use a big fancy word, which I would spell correctly if I wasn't trying to go so fast. E-A-R-E. However,
Is that a big fancy word?
I think it's a modestly fancy word. It's a mathy word. However,
Indubitably.
use your own fancy word. When broken into individual programs, or you could say, subgroups, the women are more likely to be admitted than men. So let's say guesses for program A. What is one example of a major where there is a lot of interest from men and lesser interest from women? I can think of at least two. Engineering.
That number's changing.
That number is changing, but on average. Math, especially if you're talking about the graduate school level, right? I wasn't thinking engineering, but also computer science, Do you guys buy all that? All of those might have a lot more male applicants than female applicants, right? Guesses for program B? Yeah, there's, I would say something probably,
Nursing.
Psychology.
yeah, I was gonna say psychology. I think nursing probably is still pretty female dominated, as is teaching, actually. I would go with both of those, and you probably can speak to the nursing thing as a lot here. Teaching definitely, especially the elementary level, is definitely really female. Psychology, maybe anthropology.
No, I thought psychology was one of the ones where it was switched, where
Yeah, but I think it's more even, but I could be wrong. Okay, as in like this is a guess. There's not a right answer. I don't know the right answer. It's a sort of like, what do you think? But something for which women apply more than men, but not drastically more. Does that make sense? Because the total is 350 versus 425. That's not hugely different, right? Elementary ed, I think that I had a friend who was in the elementary ed program, and there might have been like 20 teachers or something that were in his program, but he was the only guy. That's like a really big discrepancy.
Even though it seems I always see more male teachers, I don't know.
Yeah. Okay, that